All right, let's just dive right into it. Welcome to The Explainer. Today, we're taking some complex ideas and breaking them down so we can uncover exactly how our world holds together. Literally. We are exploring a super high-stakes topic, the mechanical properties of metals. We're going to look at what actually keeps the structures all around us, from massive suspension bridges to the airplanes we fly in, from just suddenly collapsing. It's an absolutely fascinating journey into the invisible forces holding our modern world together.
So, think about the last time you were on a commercial flight, looking out the window as the plane hit some nasty turbulence. You probably saw that wing bouncing up and down, right? It kind of makes you wonder, how do engineers actually guarantee that wing won't just snap clean off? Well, understanding how materials respond to forces, whether that's tension pulling them apart, compression squashing them together, or shear forces sliding them out of place, well, it's quite literally a matter of life and death.
To get to the bottom of this, we're going to break down this complex materials science step by step. Our agenda for today is 1. The engineering dilemma. 2. Stress, strain, and elasticity. 3. Pushing past the limit. 4. Toughness and failure. 5. Measuring metal hardness. And finally, 6. Designing for safety.
All right, starting us off with Section 1, the engineering dilemma.
Okay, so whenever a load is applied to a material in the real world, we really have to look at two fundamental metrics. Those are stress and strain. Stress is essentially the invisible force we're applying, like the bending tension on that airplane wing or the massive torsion twisting a car's axle. Strain, on the other hand, is the visible result. It's the actual physical deformation, the stretching or squashing that happens directly because of that stress.
Moving right along to Section 2, stress, strain, and elasticity. Now, what's really fascinating here is that at very low levels of stress, metals behave highly predictably. And this brings us to Hooke's law. Hooke's law basically states that in these early stages, stress and strain are directly proportional to each other. So, if you were to graph them out, they'd form a perfectly straight line. And the slope of that line? That's a constant known as the modulus of elasticity, or Young's modulus. You can really just think of this as a measurement of a material's stiffness, or how well it resists being stretched out of shape. The higher the number, the stiffer the metal.
And honestly, what's truly wild is the sheer range of stiffness across different metals. Take tungsten, for example. Its modulus of elasticity is a massive 407 gigapascals. I mean, it is incredibly stiff and resistant to stretching. But then, compare that to magnesium, which sits way down at just 45 gigapascals. So if you're an engineer designing a component that absolutely positively cannot flex, you are looking very, very closely at these numbers.
But hey, as long as we're operating under Hooke's law, we're safely in a zone called elastic deformation. It's basically the rubber band effect. Think about it. When you stretch a rubber band and let go, it snaps perfectly back to its original shape, right? Well, metals do the exact same thing on a microscopic level. The inner atomic bonds between the metal atoms stretch slightly under the stress, but the second the load is released, those bonds pull right back. The piece returns perfectly to its original shape, and there is absolutely zero permanent damage.
Which brings us to Section 3, pushing past the limit.
Because the real question is, what happens when we push a metal too far and those tiny interatomic bonds finally break? Let's map out exactly how this builds across a metal's lifespan under intense pressure. We start at Step 1, elastic deformation, where the stretch is just temporary. But if we keep pulling, we hit Step 2, yielding. This is where permanent change begins. If the force keeps coming, we climb to Step 3, tensile strength, which is the absolute maximum load limit the metal can take. And finally, if we still don't let up, we hit Step 4, fracture. The metal completely snaps.
Let's actually zoom in on Step 2 for a second. Yield strength is the stress level where we officially leave that safe rubber band zone and enter the zone of plastic deformation. At this exact point, which is typically measured in the lab at a tiny 0.002 strain offset, the metal permanently changes shape. Think of an ordinary metal paperclip. You can bend it slightly and it springs back, right? That's elastic. But if you bend it just a little too far, well, it stays bent. You've exceeded its yield strength. Those interatomic bonds have literally broken and reformed with brand new neighbors.
Now, if you keep applying force past that yield point, the metal actually gets stronger for a little bit as it stretches, until it hits the absolute peak of our stress-strain mountain, the tensile strength. This is the maximum stress the structure can possibly sustain, period. And what's fascinating is what happens next.
Right at this peak stress, the metal begins to visibly narrow in one specific spot. Engineers actually call this necking. And once that little neck forms, all the subsequent stretching is totally isolated to that one weak point, and the stress required to stretch it actually drops until the metal finally fractures right at the neck.
All right, that brings us to Section 4, Toughness and Failure.
We know the metal is going to snap eventually, but exactly how does it fail? Well, this is exactly why engineers prefer certain materials over others. We basically have ductile metals versus brittle metals. Ductile metals, things like copper or aluminum, experience a whole lot of plastic deformation before they break. They stretch, they bend, they neck down. Engineers absolutely love these because they're forgiving. If a building or a bridge is experiencing way too much stress, a ductile metal will visibly bend, giving us a clear warning of danger long before a catastrophic failure. Brittle metals, on the other hand, they fracture with less than 5% strain. They barely stretch at all before they suddenly and violently snap, with almost zero warning.
So you can see why a truly great structural metal needs a careful balance, a concept engineers call toughness. Toughness is essentially the ability of a material to absorb energy and deform plastically before fracturing. If you were to look at a graph of stress and strain, toughness is actually the total area underneath that curve. To be truly tough, a metal must have the perfect combination of both high strength, so it can take a massive amount of force, and high ductility, so it can stretch out and absorb energy without just shattering into pieces.
Moving on to Section 5, Measuring Metal Hardness.
We know how metals fail under massive tension, but how do engineers actually test these properties quickly and cost-effectively in the lab without completely destroying the sample? Well, they use hardness tests. Hardness is really just a material's resistance to localized plastic deformation. Think of it like a tiny dent or a scratch. The Rockwell test is the most common one. It basically measures the depth of an indentation made by applying a minor load followed by a major load. Then there's the Burnell test, which uses a heavy 10mm hardened sphere. And if you need to test a microscopic region or maybe a really brittle ceramic, you'd use micro-indentation tests like Knoop or Vickers. These carefully press a tiny diamond pyramid into the surface. By simply measuring the size of these tiny dents, engineers can actually estimate a metal's overall tensile strength. Absolutely no snapping required.
Which finally brings us to Section 6, Designing for Safety. How does all this lab data solve our original engineering dilemma in the real world? Well, here's the fascinating math behind your everyday safety. When engineers build that airplane wing we talked about earlier, they don't just calculate the maximum stress it can take and call it a day. No way. They calculate a safe working stress. To get this, they take the yield strength of the material, remember that's the point where permanent damage begins, and they divide it by a factor of safety. This factor is usually a number somewhere between 1.2 and 4.0. This crucial math ensures that the day-to-day forces the structure experiences never even come close to the material's actual limits.
I want to leave you with this incredibly thought-provoking quote from the source material. Instead of asking, what is the fracture strength of this alloy, the engineer should ask, what is the probability of failure? The truth is, even with the absolute best testing, there is always microscopic variability in materials. Literally, no two pieces of steel are exactly identical. True engineering isn't just about knowing exactly when a pristine piece of metal will snap in a lab. It's about utilizing all this data to anticipate the unknown, mitigate the odds of catastrophe, and keep us safe in a totally unpredictable world. Definitely makes you look at that airplane wing a little differently now, doesn't it? What other invisible forces do you think are holding our world together right now? Thanks for exploring this with me today on The Explainer, and keep your curiosity strong.